Okay, so let's start with the space efficient sequence alignment. So this is one of the optimizations we would like to do to perform sequence alignment uh, in as the namespace as less space as possible. Right. Currently, we would require quadratic space if n and m are length of the two sequences. We will require order of nm space to store all the backtracking pointers and to store all the entries, the best or the longest path till a particular node. Right. Can we do better than that? The running time order of nm seems like something that we cannot get away with, but can we do better in terms of space? And the idea there is to look at the middle column of the alignment, and if we magically someone tells us what is the best node or the node through which the longest path passes through, right, from this original source node 0, 0 to n, m, then we can then run two subproblems. So we can do this divide and conquer and then run two subproblems, right? So if someone tells us that this is the best node, then we can just run one subproblem that looks at this as the source node and this as the destination node, and similarly another subproblem which looks at this as the source node and this as the destination node, right? So this is the overall source and this is the overall sink, and so knowing this would help us break it down into two subproblems. And will this help us save space? That is the question we are going to ask. Yes. Okay, but we are now back in the space where all the matches are +1, the mismatches are minus mu per mismatch, and then the gaps indels are minus sigma per gap. Okay, we don't have this epsilon complication for now. Now if you know this, then to figure out this path, then you have to just look at this particular subproblem, and then you have to look at this particular subproblem and then figure out the best path shown here by looking at all the paths within that area using a DP algorithm again, right? These are just two rectangles that we are trying to analyze, and that is what is illustrated here. This is divide and conquer. You know the middle node, someone tells you the middle node, and then or you figure out the middle node through which the best or the optimal path passes. Then you run this subproblem, you then run this subproblem, and then you are done. Okay, now the question is, how do you find the middle node in linear space? Okay, if you find the middle node in linear space, then you can figure out all the nodes, then you can recurse, I mean you can divide this problem into two other subproblems by looking at further the middle node on the left side, the middle node on the right side, and then you can keep on doing it and you can figure out all the nodes along the path. Okay, and yeah, so can we find the middle node in linear space? And then let's review two things. Okay, where is the space requirement of order of nm coming from? Okay, so that is really coming from storing all the backtracking pointers and not really in finding the score of the optimal path. Okay, why is that? So the backtracking pointers for every node, you need to know which node you are coming from in terms of the maximum. You are taking maximum among three nodes, right? So for each one of them there is like this edge, and this edge, so you need to store which edge contributes to the maximum, right? So that there are order of nm, and that seems to be the reason that we have order of nm memory. But for calculating just the score of the longest path, you don't have to store all the scores you have computed so far. So you find some score, this is 0, maybe you just find out that this is also 0, this is 0, let's say, and then this is 1, and then you just keep filling these, right? But if you go in a certain order, then in order to figure out this node, all you need is only these last two columns, right? In fact, you only need these three nodes, right? You don't need any other nodes. I mean, specifically the first column, the second column, all of them you don't have to keep it while you are calculating what is the best score in the last node, right? You can throw them away, right, as and when you compute them. So this column is going to be, let's say you go in this column wise ordering, you compute the best score for the first column, then you compute the best score for the second column and third column. That will be a valid topological ordering, right? You can go column by column at a time. You can also go row by row at a time. That will also be a valid topological ordering of this directed acyclic graph, right? And so for simplicity, let's say we go by column, and after you have used this first column to compute the second column, then you can throw away the first column, because this column is only needed to compute the next column, right? So you have used this column to compute this column and then use this column to compute the next column. This can be reused. The space you have for the first column can be thrown away, and this can be reused for the second column, right? And then when you go from this to this, then you can throw away the previous column, right? Let me just name these columns. So this is column 0, column 1, column 2, and so on till you have column m, right? You only need to keep two columns at the same time. First you need to have 0 and 1 column. You fill up all the 0th column entries, and then you have all the first column entries, that is 0 is needed to compute the first column. Now when you go to 1 comma 2, you don't need 0, you only need 1, and then so you can store these new values in the same space and then use up this. When you go from 2 to 3, then again you can throw away 1 and you only need two columns, right? So the second column and then the third column is going to be computed using all the values in the second column. So you only need space for two columns at a time, and that is why if you don't have to keep in backtracking pointers, then you can keep on throwing this or recycling these arrays, and you only require order of n memory. Okay, so I hope that is clear. So then now the natural question is, okay, I don't want the longest path score alone, I want the actual longest path. Can that be done in order of n time? Okay, so the fact that you can find the length of the longest path in order of n time follows from this topological ordering, where you store columns at a time and you only need to have space for two columns at any point in the running of this algorithm. Okay, now to figure out the backtracking pointers, can something clever be done? Okay, and this is essentially repeating this order of n argument. You only need to have two columns at a time, okay, to figure out the best path. You can see here that 0, 1, 1, 1, 2, 2, 2 is used to compute this 0, this 1, this 1, this 1, this 2, this 3, and this 3. After this, you don't need this column, so you can skip it and then you can go directly to this. Okay, and finally you find out that the longest common subsequence is 4 between our two sequences, like we have seen before. Okay, now the question is, can we find the middle node without constructing the longest path? Because the constructing the longest path will require getting all the backtracking pointers, and we have seen that backtracking pointers will again use up all the space, order of n, quadratic space, right? And in order to understand this, we go back to our decomposition of this problem. If this were the node through which the longest path goes, then what will be the cost of the best path that goes through this node? Okay, so the longest path that goes through this middle node will be the longest path that goes from the source to this middle node, and the longest path plus the cost or the length of the longest path that goes from this node to the sink node, right? So we call that as an I path. Okay, so I path is the longest path from the source to the sink that goes through the ith node in the middle column. Okay, so for instance here, this is a 4 path. Again, we are starting numbering from 0, so this is 0, 1, 2, 3, 4, so this is the 4th row, right? And this is 5, 6, so n equal to 6, right? And the column is again 0, 1, 2, 3, 4, 5, m is also equal to 6. Okay, so you look at the middle column, column number 3, right? And then you are looking at, if this is the node, 4th node that you are looking in this column, ith node. So the 4th path is the path that visits through 4 of all the paths that visit through 4 from source to sink, which is the longest path. Okay, is that clear? Yeah. So, and the value of that will be the best path from source to that, and then from that to sink, right? So that in this particular case, the length of 0, this 0 path, right? Length of 0 is the length of an I path, so length of 0 will be 2. Okay, because there is only really one path that will go through this, right? And to go through this node, so from here to here, there is only one way to reach from source to this node, right? So this node is essentially the node 0 comma middle column, right? Middle column is 3rd column. So this node is indexed as 0 comma middle. So you have only one way of going from source to this 2 nodes. So that is all these blue edges. There are many ways of going from this 2 to this final sink node, and the best way of going is shown in these blue and green and red arrows. Okay, and so those red arrows are +1 and +1, and so you get +2 is your best path that goes through the node 0. Okay, length of 4 is going to be the length of a 4 path, or the best path that goes through this node 4, right? And here again there are many ways of going from source to 4 and from 4 to sink. if you run the dynamic programming algorithm from source to 4 or 4 to sync, then you will have that this is +1 and +1. So this is 2 to go from source to 4, and then another 2 to go from 4 to sync, and so you will get 4. Okay, that is the illustration. Similarly, you can write down all the lengths. So length of 0 path is 2, length of 4 path is 4, length of 5 path is 3, length of 6 path is 1, and so on. Okay, so you can figure out all of them. And then you now know the middle node, right? If you have figured this out, now you know the middle node. The middle node is going to be whichever is the highest among all of these nodes, right? Highest score among all of these nodes in the middle column, right? So, and how do you figure this out? Like I just said, you just figure out the best path or the longest path from the source to I and from I to the sink. Okay, we just need to know the length of the longest path from source to 4, and similarly the length of the longest path from 4 to sink. Okay, we don't need to know the exact way in which you reach 0 to 4 or 4 to sink. Okay, which means that we can use our order of n or linear space algorithm for kind of finding the length of the longest path, right? Because we have just seen that you only need to keep 2 columns at a time, and you can reuse those same 2 columns, right? And that one run can give you the best values of all of these nodes, because the source is always the same, right? So source is always the same, it's only the middle node which keeps changing. So if you run one DP algorithm from source all the way to this node, right, then you will get the best or the longest path from source to each one of these nodes. Okay, and you have to use only linear space because you have to only operate 2 columns at a time. Okay, so then that is the first half. The other half is you want to go from this node to the final sync node. There is a small trick you can do to repeat the same algorithm. Can you think of that trick? Yeah. Or if there are anything unclear, let me know. Yeah. So what I have just said so far is you can run the normal DP algorithm, right? That uses 2 columns at a time. So this column 0 and 1, right? And then this column 1 and 2 after throwing away 0, and then the column 2 and 3 after throwing away 1. Then you will have all these values which are the longest paths from source to all the nodes in the middle column, right? That is our exact same algorithm that we used to run all the way to find the length of the longest path till the sync node, but here we just stop midway. Okay, and then we get all these values 2 3 3 3 4 3 1, and then by looking at these values, then we can pick the best node 4, and we know that that is the middle node, right? So that, but that only gives you kind of one part of the equation, right? That only gives you this from source, right? If you run it from this source and then stop your original DP algorithm at this middle column, it will give you all the from source. Okay, but in order to know this 2 3 3 4 3 1, you also need to add it to 2 sync, right? You need to know the best path from each of these nodes to sync. Okay, exactly, yeah. So you can look at this second half. You can treat the sync as the source, and then you can basically invert the direction of all the edges. So if it goes from left to right, you make it go from right to left. If it goes from top to bottom, you make it go from bottom to top. So then you will start from this node, and then you will end up in all of these other nodes. Okay, so that will give you 2 sync of I. Okay, so that also you can again do the same thing. So you just start with these last 2 columns, right? So last column and last but 1 column. So this is column 6, this is column 5. Then you go to column 5 and 4, throw away this. Then you go to column 3 and 4 and you throw away 5, and then you will get all the 2 sync of the middle column. Then you take those 2 vectors and add, you will get length of I, which is this 2 3 3 4 3 1 that is shown here. Okay, so yeah, this should be 2 here, because if you want to include this node, you are essentially saying that you want to have ATT CAA, right? And then you want to be able to delete all of these GAA, because these are the only way to go here, or actually inserting, I'm sorry, you have to insert GAA, right? And then you have ACG.
Delete 2T.
Yes. ACG, sorry, AC, and then you can put it anywhere here, yeah. Yeah. So then you will be getting this, you will be deleting 2 T's, and then you will be having this C here, and then you'll be having, so you have covered till here, then you'll be having AG, and then you'll be coming down like this. All right. So this should be 2, yes. Okay. So using this the usual DP algorithm, you start with 0, 0 and then run it as usual using only 2 columns at a time, reusing the space, and you stop at the middle column. That will give you from source of I for all I, right? Using only half of the area, right? You just, if the whole thing is m and n, so with order of nm over 2, you are able to time you are able to, and with order of n time linear space, right? So the number of the length of columns is n, right? You need 2 columns. With this space and with this time, you are able to figure out from source of I for all I, right? Similarly, like what Ritvas was saying, so you just take from sink, and then you basically run the reverse problem, treating this sink as the source and then going on the reverse direction of these edges. You will be able to get 2 sink of I, because it's exactly a symmetric problem for all I again, and then you add it up, you get this length, and using that you can figure out that this is the best middle node, right? The longest path will go through this particular middle node. So this is what we just said. Each of these can be separately computed and added up. And here they have correctly computed it as 2 and 0, and then added up would be 2. But in the previous thing, they wrote this as 1. Yeah, so that's type. So how much time did it take to find the middle node? Like I was saying, order of nm over 2, right? So there is area over 2 here and area over 2 here, right? And then so that means that you have in total 2 times that, so that you have you are spending time order of nm, right? Area is nm, so you have nm over 2 plus nm over 2, and then so the total time is still, or the space is still order of sorry, the time is still order of nm, right? The space is now become linear order of n, because you are just doing this 2 columns at a time, right? Okay. So this progress is laughable, because in the sense that yes, we have made the space better order of n, but we have only found out one middle node, right? The middle, all the other paths from the source to this middle node and this middle node to the target, the sink, we haven't figured out yet, right? And then we have spent already order of nm time, and now we have to run several other sub problems, and if each of them takes order of nm time, then we are in a cubic running time, if you will, right? Order of n squared m. So is that really a concern? Because this looks ridiculous at this particular point in time. To find one node in the optimal path, it has taken as order of nm time and order of n space. Okay. Now we have these 2 sub problems, right? These 2 sub problems are the ones that we need to solve now. Will it again take order of nm time, or will it take better than order of nm time, right? That is what we would like to understand. And this black node can be anywhere along this middle node, right? So but this seems to be the case that is the worst case. So you want to divide it into equal size sub problems. If you are over here, right, then you really have to solve the sub problem that is all here, this one, right? That will be the area over 2, and then this sub problem is only one line, so that is a linear sub problem, right? So it turns out that the worst case will happen when this middle node is exactly in the middle. The worst case running time will happen, right? If you have things such as skewed ones such as this, then you will be able to argue that this will only take, let's say your black node is over here, right? Then it will take order of nm over 2 plus this is m over 2, right? Because this is half of m. This is the mth column and this is the nth row, right? And so you'll be able to say that this is order of nm over 2, right? But let's look at this scenario where you are in the middle and you have balance of problems on both sides. Okay, so how much time will that take? When you have such balance of problems, you have area over 4 on this side and area over 4 on the other side, right? So meaning nm over 4 and nm over 4. And so totally you have area over 2, right? So what used to take to find this black node, right? It used to take us order of nm time, but to find the black node in this middle column, right? This middle column or in this middle column, it will take half that time, okay? To find both of them, right? So you can find these black nodes, these 2 additional black nodes, in time just order of nm over 2, or time area over 2. Okay, and then you keep on doing that, right? So time to find 3 nodes is order of nm plus nm over 2 now. So initially we found 1 node, and then now we have on those 2 subproblems we have found 2 additional nodes for a total of 3 nodes. Okay, now we can recurse on this. I mean, this is a divide and conquer problem. Now you have this subproblem over here and this subproblem over here, right? And then you have another subproblem over here and another subproblem over here. So now we have 4 subproblems instead of 2 subproblems, right? But the advantage is that each one of them is going to be now area over 8, right? In the worst case. So then you have these subproblems, and all of them will give you all of them are of area over 8, and times 4 is going to be area. Actually, let's see. Yeah, 4 times area over 8 will be area over 2, right? How come they say it's area over 4? Okay, some other typo here. This has to be, so area over 8, 8, 8, 8, or is it over 16? 1, 2, 3. This has to be, this is area over 16, right? Because, okay, sorry about this. So this is area over 4, and then each one of them you are dividing it into 4 pieces, so then it will be area over 16. Yeah, and then 4 times that is area over 4. Yes, so this one has to be 16.
So like
yeah. Okay, I'll start from here. Okay, so you have now found 3 nodes in time order of nm for finding the first node, and nm over 2 for finding this black node and the other 2 black nodes, right? So now we have these 4 other subproblems that I have drawn as these rectangles, and okay. Okay, so we have taken up nm to find the first black node and nm over 2 to find the other 2 black nodes. For finding a total of 3 nodes, we are finding in order of nm plus nm over 2 time. And then now let's say we have to solve these subproblems. This is the first subproblem, this is the second subproblem, and this is the third subproblem, and this is the fourth subproblem. And each of these areas, you are taking an area which is area over 4, and then you are just splitting it into 4 boxes, right? So then this is going to be area over 16, area over 4 divided by 4 will be area over 16. Similarly, this will be another area over 16, this will be another area over 16, and another area over 16. So the total time is going to be 4 times area, which is nm over 16. So it's going to be order of nm over 4. Okay, area over 4, right? So those are the area of all these orange boxes here, and that is what we need to do to figure out another set of 4 more black nodes. Okay, and you keep on repeating it until you have figured out the black nodes, which is the nodes in every column that the longest path has to go through. Okay, so these are the other black nodes, and then you have all the black nodes that you have figured out. And these are all the other subproblems between. I mean, some of these black nodes, all these columns are already done. This column is done, this column is done, this is done. So similarly, this column, this column, this column, all of these are done now, right? So then you just have to figure out between these yellow ones are the ones that are remaining, and some of these yellow ones are just these little boxes, and so you can directly connect them with the edge that connects them immediately. So this is the edge, this is the edge, and so on. Between this black node and this black node, you have to figure out what is the best path. And all of these subproblems again will take like initially you took area, and then the next 2 nodes it took area over 2, the next 4 nodes you took area over 4, the next 8 nodes you will take area over 8, and so on. And you will see that this is a geometric series, right? So it has a certain ratio that keeps on getting reduced by a factor of 2, and so that you can see that it is 2 times area. Another visual way to see it is this is the first pass which takes area, and then you have half the times area, and then you can stack up 1/4 over here, another 1/8 over here, 1/16 over here, 1/30, and so on, and it will never go more than 2 times the area. right? This is just a geometric series that just follows from this inequality, right? And it just essentially, it's not even strictly less than 2. If you have an infinite series, it converges to 2, right? So you can see here that even though we were initially quite concerned that it may take much more time than order of nm, we are just saying that this whole process will only take order of 2 times nm, right? Which is the constant 2 is not that bad if n and m are very huge. So order of nm is our final running time, and our space all throughout has been only order of n. Okay, so now we have a linear space algorithm that runs also in the same running time, order of nm, without increasing or blowing up the running time. Okay, so this gives you all of these middle nodes, and from those middle nodes you can figure out the whole path. But then there is a slightly different formulation that you may want to figure out the exact edges also, right? So for instance, I told you that there was this one case where the middle nodes are known here and here, but then between them we need to figure out also the exact edges to follow, right? So this edge is called a middle edge in some sense, right? So there is a slight variant of the algorithm that we have seen so far that will figure out the middle edges, and then that will give you directly the best alignment from the source to the sink node. Okay. And again, the middle edge is simply the edge in an optimal alignment path starting at the middle node. Okay, so from the middle node, what is the best path will take this edge or this edge or this edge? Which of the 3 edges is it going to take? Okay, that is the middle edge. Okay, so the optimal path will go through which of these 3 edges starting at the middle node. Okay, optimal middle node. So then this is the way to formulate that problem. So middle edge in linear space problem is you want to find the middle edge in the alignment graph, meaning the middle edge taken by the best or the longest path from the source to the sink, right? Input is again 2 strings and a matrix score. So the score can be a general scoring matrix. We have seen that in DNA it is 5 cross 5, right? ACGT and dash cross ACGT and dash. Output is a middle edge in the alignment graph. Basically the edge that is taken by the longest path from source to sink. So here is the middle edge in this particular alignment, right? It's just leaving this middle node. Okay. And in this particular sub problem, this is the middle edge, right? And this is the middle node. Similarly, in this particular sub problem, this is the middle edge and this is the middle node. Okay. So once you know the middle edge and then the middle node, then you just have to work on only these orange sub problems, right? Because the edge is given to you and then you have to work on these orange sub problems. Initially, you have to work on these blue sub problems. In the second level, you have to work on these orange sub problems. And then the whole algorithm looks like this, right? And then you can keep on recursing it until you have figured out all the middle edges, and that gives you the full alignment path. And this has a similar flavor as the linear space algorithm that we figured out for finding just the middle node. Okay, so without going into too many details, the full algorithm is or without going into too much illustrations, the full algorithm is given here, right? Which is, you have these 4 values that will tell you the coordinates of the sub problem that you are looking at. What is the top and the bottom rows and the index of the left and the right columns, right? And then you are going to split it into 2 different sub problems after you have figured out the middle node and the middle edge, right? So if you will, so this is your top row, this is your bottom initially, and this is your left column, and this is your right initially, right? So this is your top row and bottom row and left column and right? Now once you have figured out the middle node and the middle column, this is the column middle, right? And this is the row which is called as middle node, right? Middle will point to this particular column, middle node will point to this particular row, right? So then your new sub problems are going to be the top comma left will be the same, but here this will become middle node comma middle, right? That is what is given. Top and left will be the same, right? But the bottom and right are changed to middle node comma middle, right? So that is what this is. And similarly, here it's going to be depending on this edge, right? So if this edge goes down, then this is going to be middle node plus 1 in terms of the row, right? If the edge goes like this, then it will stay at middle node. If the edge comes down here, again it will be middle node plus 1, right? So the subproblem, this blue subproblem, will depend on what the middle edge is, whether it is this edge, horizontal edge, vertical edge, or the diagonal edge. Based on that, this starting row will change, right? The ending row and the ending column are always going to be bottom comma right. Right, that will remain the same. And again the middle, the column will again be depending on whether it is the right edge or the diagonal edge. It is going to be either middle plus 1, or it is going to, if you take this edge, then this is going to be the full blue subproblem. It is going to stay at middle. Okay, so this, all of this logic is captured in here. If the edge is diagonal or going right, then the column is advanced, middle becomes middle plus 1. If it is a downward arrow or a diagonal arrow, that is the best middle edge, then the row is advanced. Okay, middle node plus 1. So this is advance the column, this is advancing the row. And then you have bottom and right are the same, so then you have middle node and middle, which is the advanced row and column. Okay, so these are the two subproblems, and middle is always going to be the middle column between left and right. And we can take a ceiling or a floor, it doesn't matter. Here they have taken a floor. If you have a value like 5.3, then it becomes 5, right? Yeah. So this is a divide and conquer method. It will take linear space and it will take order of 2 times the area, 2nm. Okay, and it will also figure out all the edges in the particular path. Okay. So that completes our discussion of pairwise alignment, all the different variants, local and global variant, simple scoring matrices, complicated scoring matrices, and space efficient sequence alignment.